Hello, my name is Chris Thrawn. I teach math at Texas A&M University, Central Texas. I'm going to talk to you today about Voila proofs with iteratively inscribed similar triangles. This is an amplified version of a talk given at the 2011 MathFest at Lexington, Kentucky. I decided to break the talk up into 3 bite-sized pieces to make it easier to digest. So why is it great to iterate? What's the big deal about iteration? Actually, iteration is an ancient method. Archimedes used it to find the areas of objects without using calculus. Very clever way that he used. In particular, Archimedes used the method of exhaustion to find the area of this parabolic segment. Consider this parabola here. And he found the area inside this parabolic segment in terms of the area of this triangle. Now this is an inscribed triangle, but it's a particular inscribed triangle. It's the triangle inscribed within the parabolic segment that has the maximum altitude. So we'll be doing that in this section of the talk in the next slide, showing how Archimedes related the area of this triangle to the area of the parabolic segment in a iterative fashion. All right, iteration is also a modern method. Fractals rely on iteration, and fractals are now part of the standard high school geometry curriculum. Let me remind you how fractals work. This particular fractal is called the Koch snowflake, and the way it's created is first you draw a triangle, then each segment of the triangle you replace with this figure. Basically, it's a segment with a blip in it. And you do that with each of the segments of the triangle. So you get 3 segments with blips. They actually look like another star. Then the iteration comes in when I take every one of these segments in my new star, and I do the same thing. I replace that with a similar figure, a section with a blip in it. And then from this snowflake here, I do the same thing. Each straight segment here becomes 1, 2, 3, 4 segments in here, and so on. So each time I have 4 times as many segments in the succeeding figure. Iterative method leading to a very interesting design. All right, as we can see from these 2 examples, that methods with iteration are actually visually appealing and also amenable to modern software. Software packages like Geometry Sketchpad, and there are others, are able to take geometric figures and perform transformations on them, and then repeat those transformations. So they're very easy to use to make iterative constructions. Iteration is actually a hugely important technique in modern analysis. When finding fixed points, it's the standard technique. You try to find something close to a fixed point and find a way to improve it, and then successive improvement by iteration. Iteration in dynamical systems, a number of places where iteration appears. Very, very important method. So lastly, iteration can lead to proofs that are visually immediate, and that's what I really want to focus on. I call this type of proofs Voila proofs. Now you notice there's a caveat. Sometimes the technical details of these proofs can be nasty, but we won't let that bother us. Okay, so let me use iteration to prove Archimedes' area, the area of the parabolic section. And let's go ahead with that. Here's our first frame in the proof. You can see the original parabola. You can see the original triangle inside. Now that triangle, as I said, is the triangle with maximum altitude. So by altitude, I mean the perpendicular distance from this base of the triangle to its apex. So this triangle is the inscribed triangle that maximizes this perpendicular distance. And if you think about it, that must mean that the tangent to the parabola at the vertex point must be parallel to the base. So think about it, that is true. That being the case, we can draw this parallelogram And the parabolic section is inscribed in the parallelogram. Now, we're not going to find the area of the parallelogram, but we're going to use this to do something very tricky and very clever. Going on to the next frame, we're going to perform a skew transformation. Now, what do I mean by a skew transformation? Well, think of this parallelogram here as consisting of several parallel vertical segments. Now, these segments are not lined up. The farther along you go in the x direction, the farther down these are marching. But suppose I try to line these segments up. In other words, let me shift this one down so that the lower point just touches the x-axis. Let me shift the next one down so that its lower point just touches the x-axis, and so on. I'll have to shift this one up so that its lower point touches the x-axis. If you think about what I'd have all of the segments lining up like this. So this is a skew transformation. In fact, that parallelogram is shifted into a rectangle. And I'm not just shifting the parallelogram, I'm shifting all the points in the parallelogram the same way. So, in fact, the entire parabola and the triangle will be shifted correspondingly. All right, that's a skew transformation. Now, it's somewhat intuitive that a skew transformation will not change any areas. Well, for instance, the parallelogram, it certainly won't change the area of the parallelogram. Think about the base and the height of the parallelogram. Well, the base and the height of the parallelogram are the same as the base and the height of the rectangle. Of course, I'm measuring height here along the x-axis, and I'm measuring the base along the y-axis. But if you think about it that way, the area of the rectangle and the area of the parallelogram will be exactly the same. And in fact, all areas will be the same. The area of the transformed triangle will be the same as the original triangle. The area of the transformed parabolic segment will be the same as the original parabolic segment. In more advanced terms, a skew transformation has Jacobian equal to 1, so it preserves area. So if you didn't understand that comment, that's fine. But I think you can appreciate intuitively that the skew transformations will not change areas. Now, what's the advantage of this? This new parabolic segment looks a lot easier than the original one. And the new triangle looks a lot easier than the original one. Just easier to get at, easier to use. So I'm going to work now, from now on, I'm going to work with this new and improved parabolic section. Okay. So if you remember the original picture that Archimedes used, what he does now is he breaks each segment in half, each x segment in half, and draws another triangle. And he's going to do the very same thing with these triangles. Well, I got a little ahead of myself here. What I meant to say is that we now have 3 triangles. We have our original triangle. Then we have 2 triangles coming off that original triangle. And so we have a total area of 3 triangles. I'm going to break those 3 triangles up into a different way as a trapezoid plus a triangle. Okay, if you look again, you can see how the 3 triangles can be broken up into trapezoid plus triangle. Just to make it very clear, the area that I'm dividing up is this straight line, this straight line, this straight line, this straight line here. It's kind of funny shaped figure. It's actually a 1, 2, 3, 4, 5. It's actually a pentagon. We can break it up as trapezoid plus triangle. Now I'm going to leave this as an exercise for the reader to show that the area of this funny pentagon is actually 1 1/4 times the area of the original triangle. It's not that hard to show. Just thinking about ratios of things in the parabola. One thing to notice is that in a parabola, if I go from here to here, I'll go up a certain height. Now if I go out twice as far, I'm going to go up 4 times as far. Same on the other side. If I go from the vertex out to a certain distance, I'm going to go up a certain distance. If I go to the vertex out to twice that distance, I'm going to go up 4 times as far. You can actually use those facts to show, taking advantage of this breakup, to show the fact that the pentagon has 1 1/4 times the area of the triangle. Now that's kind of a key step in the proof. Okay, now once we have that, we're almost done. Here's our last panel. Notice that each one of these side triangles, the little side triangles, is now in the same situation as the original triangle, the original red triangle. Well, I can draw parallelograms on these side triangles. Again, the side triangle is this straight line to this straight line to here. I can draw parallelograms around those. There's parallelogram there. And that parallelogram is analogous to my original parallelogram up here. I can perform a skew transformation on these parallelograms. There's one parallelogram there. There's another parallelogram over here. So I can perform skew transformations on those parallelograms successively. I can put in more triangles, just like I did over here, except I'll be putting in smaller triangles. I'll be putting in another triangle here, another triangle here, another triangle here, another triangle here. Those new triangles will have 1/4 the area of, altogether we'll have 1/4 the area of these triangles that I added at the second stage. And what you've got is an infinite iterative process. Every time you're adding 1/4 times as much. So if you think about it, you're going to end up with this series. You're going to end up with a series in red down in the 4th panel. And that's going to give you 4/3. The sum of all the areas of these triangles, this iterative process, is going to give you 4/3 times the area of the original triangle. Now notice that we're actually using similarity. After the skew transformation, all of these pictures are similar. So we're using iterativeness and similarity, just like we will in the succeeding proofs. So that's the end of part 1.